some things to work on if some of you folks are interested in working on data-driven methods or power systems control. This is kind of a snapshot of where my research is at the moment, including what I would call preliminary results, and it ends with what I would describe as the main question I'm working on right now in terms of power system stabilization. So I just started at the University of Melbourne. That's very far away. It's the southeast corner of Australia. It's a good place to visit. If you ever want to come visit, you're welcome. So make this small so I can see the slides. So this is a slide that I made at the end of my PhD, trying to make sense of power systems research. In particular, it makes the point that power systems research scans multiple timescales. So it goes all the way from microseconds, if we consider switching frequencies of high-performance inverters, to decades, if you consider the planning decisions that we're expected to make. So if you're interested in controller optimization theory, I'm certain you can find something to apply what you're working on somewhere in this graph, in this plot. This was my PhD focus, and my PhD I focus on distribution network variability and wind and solar variability, particularly on distribution networks and how do we control active distribution networks so that we can get more EV chargers or rooftop solar plants onto the distribution network. I left this slide in this talk so that I could point out that the bottom portion, the state estimation, parameter estimation, and topology identification work was heavily influenced by Deep's work when I discovered that in my PhD, but he's not here, so he doesn't get that shout out in person. Anyways, this was the focus of my postdoc research. In my postdoc, I focused on dynamics and specifically how do we stabilize the electric grid on faster timescales when we lose the inertia from rotating machines. So if you work in power systems, this won't be surprising to you. If you don't work in power systems, I'll give a bit of an explanation in a bit. But it's my hypothesis and many others as well that much of the burden for this loss of inertia will fall on the high-level inverter control. So how do we control these inverters so that the grid stays stable, even if we're losing the dynamics of rotating machines? My research is broader than that. I'm also interested in markets, including day-ahead and real-time markets, but this talk will stay focused on grid stability and high-level inverter control, because at least at the moment, I think this is something we really have to resolve in order to keep the cost of renewable electrification down, and grid resiliency. So these are some of my colleagues. Perhaps you recognize some of them. Florian gave a talk here last year, I think. I also have some of my Hitachi Energy colleagues who I've worked with in industry, and then Professor Fuso, who's a professor in Italy, and Anurag at TU Munich, who's helped me with hardware experiments. So did you all hear about this? I presume you did. This was the power outage. Everyone's like, of course, we heard about this. All Spain lost its power. This was April of last year. And these oscillations arose prior to the power outage. So they weren't actually the cause. Well, they weren't not the cause, but the formal cause of the power outage was overvoltage and decisions that were made in response to overvoltage in the Iberian Peninsula. But what led to that overvoltage were oscillations that were emerging on the Spanish grid prior to the decisions that led to that overvoltage. And one of the reasons is that they have a ton of solar panels, and the solar panels, or the inverters that connect the solar panels to the grid, were not being controlled in perhaps the best way. So here's just a bit of background for people who aren't power systems researchers. We have large rotating machines. That's gas plants, coal plants, hydro plants, where you spin a magnet inside of another magnet that's attached to the grid, and that creates electric power. Now we have converter boxes, which are constituted of many switches, and we close the switches and construct an AC waveform using pulse width modulation or some other method. So the challenge that arises is replacing rotating machines with inverters reduces grid inertia. So when you're spinning a magnet, that provides an inertial response to the grid, and those dynamics describe the dynamics of the electric grid, and they're quite large and dominant. And that's traditionally how we've analyzed power systems, and it's been the backbone of grid stability for over 100 years. So the grid was stable before we even had computers, and this is a big reason why. But now we're switching to inverters and weird things are happening, right? So we had those oscillations in Spain. Where I live now, it's in Melbourne is in Victoria, which is the southeast corner of Australia. In 2020, there were oscillations in this rural region of Australia, and they were in this subsynchronous range where the grid is quote unquote weak. And AEMO ran a report, and the concluding remark in the report is that a long-term solution could involve evolving the use of impedance analysis and monitoring techniques to identify the grid conditions for these oscillations and taking preventative measures. Go ahead.
Sorry, I just have a question. Why can't this maybe a very beginner question, but why can't you add inertia? Like, why can't you just rotate machines?
We'll get there. We'll get there.
Okay,
I promise.
okay.
This is like the next slide. But it's a great question. Because to answer your question, you absolutely can, but it's expensive.
Okay.
You absolutely can, and that's what we're doing, but it's going to drive up the cost of electricity for everybody. We don't like high gas prices, evidently. Turns out we probably don't like high electricity prices either. So this remark was written prior to ChatGPT, which is remarkable because it has a ChatGPT flavor in that it doesn't actually say anything, right? It sounds good, but it doesn't actually explain what's causing the oscillations, right? And that's not because the AEMO engineers aren't great. They are great. It's because power system stability is a very hard problem, right? So everything on the grid is connected to everything else, and the dynamic characteristic of the grid is some aggregate characteristic of all devices on the electric grid, right? So the truth is we don't know exactly what is causing these oscillations, and it's actually a very rich question, right? So where do these oscillations come from? Well, they're an emergent behavior from now, or well, previously hundreds of devices, and now thousands upon thousands of devices. So it's a very rich question. So our question as engineers isn't so much where did the oscillations come from, it's more how do we deal with the oscillations, or how do we deal with the reduction in inertia? So here we have a pop quiz. Does anyone in the room know what this is? I know it's summer break, so you thought you were, I guess you're all PhD students, so you take tests. But anyways, does anyone know what this is?
I would assume it's an engine.
Well, it's an engine without a prime mover. So it's a synchronous condenser, right? So there's a rotating mass, it's inertia built and attached to the grid. And this is actually not far from Melbourne. This was built in the 1960s. I think it was one of the first synchronous condensers. It was built for voltage support. So it provides a reactive power characteristic to the grid. Now these devices are coming back into fashion for the reason that was just asked, which is you can just build inertia. You can just attach it and you don't have to deal with the expensive burning of things to push on the turbine blades. So it could be seen as hardware that facilitates the renewable energy adoption. However, as control engineers, I'm going to assume we're all control engineers in one way or another, or perhaps optimization, machine learning theorists. It could be a symptom of a failure of control theory. So I see this as a beautiful piece of machinery, but also a sign that we're not doing our jobs, basically. So this is the economics of it for Australia. So over the next 10 years, Australia, where 1/3 of homes have solar panels. So it's this amazing rollout of rooftop solar. I think, and they're also building a ton of batteries, which are also inverter-based. However, they're also retiring a very old fleet of coal plants. And one of their solutions for that will be to build synchronous condensers. And it's a good solution. It's just not the best solution because it's expensive, right? So it's better than leaving those coal plants online, which are fragile brittle for a number of reasons. However, it's expensive. So we as control theorists are taking a time test. We're essentially, as I see it, all on the same team. And we need to come up with solutions within the next few years, basically, to avoid sunk costs in infrastructure that will then cost money to operate as well. So it's both an operational expense and a capital expense. So this is the thesis of this talk. Inertia is good, but we do not need it. Instead, we must get inverter control right. And I will present a new inverter control method that might be a good idea. I'm not saying this is definitely a good idea. It's kind of a weird way of controlling inverters, and it might be a good way to do things. We're trying to figure that out and working pretty hard on it. And that will include 2 applications. So one with industry and then one on with a couple academic labs. So back to the ChatGPT generated images. Here we have.
Before you go on, actually, I have a question.
Yeah.
So I used to also kind of say this thing about like, you don't need like day ahead and real-time markets if you can just get all your predictions perfectly right.
Yeah.
But obviously that's like an extremal
Yeah.
statement because there will always be uncertainty that causes your like predictions ahead to be. So like I just like in an analogy to this where you're essentially saying like inertia is good, we don't need it. If we just got inverter control,
Yeah.
right? Like we wouldn't need inertia at all. Like could you maybe characterize like to what extent this is like kind of like as stated is like actually what you're getting at, or is like maybe a little bit extreme or not?
I don't think this is extreme.
Okay.
I think we can do it entirely with inverters.
Okay.
I believe firmly in that, but it's going to be hard, and we can't do it in its current form. And there are really challenging questions such as protection, faults, currents, and things of this nature. So it's not easy, but I believe we can do this.
Okay.
The day ahead question is really interesting, right? Because we've always had day ahead and real time. Now we have capacity markets, and there's so many things in power systems that are the way they are because that's how they've been, right? Whereas in Australia, they don't have a day ahead market. It's the one place I know of in the world where they only have real time market, and all, of course, you still have to plan in advance, but all of the planning gets pushed onto the generators as market participants.
I see.
So yet everyone is still doing a stochastic receding horizon optimization, but there are different ways of doing it.
Yeah.
And I think we as academics have an obligation to push people, right? To say, well, I know this is the way it's done, but is it the way it has to be, or is there a less expensive way of doing it?
Yeah.
So it's a really good question, but I'm going to stick with it.
Okay.
I think we don't need inertia, but it is good if we got it. That's great.
Do you need to only do inverter control? Could you also do inverter design? Like if you are concerned about time constants, maybe you can put in some more capacitance or so.
I mean, more capacitance is great, right? Any energy storage, either a very fast energy storage like a capacitance or battery or long-term storage. I mean, essentially, power systems could be seen as an energy buffer and transportation problem, right? So anytime you're putting more storage on the system, that's great. And when it comes to hardware, which is not my specialty, it's always a give and take with control, right?
Okay.
Component sizing is inherent with inverter control. You can't really separate them.
Because you need storage for inverters anyway, right?
Yeah.
Yeah. So maybe you can play.
Absolutely.
I guess we'll assume that this is fixed.
Yeah. Yeah. So I mean, I guess I'm being a bit extreme when I say it's just a control problem, because at the end of the day, it's the hardware that provides the energy at each moment in time. But I think we as control theorists need to push that side of it. Good questions. So here's an analogy. So if you imagine two vehicles, we have a large rotating machine generator, which has a ton of inertia. And then you have an F1 car, which doesn't have a lot of inertia, but can be very fast. So this is like an inverter. And you can imagine both these vehicles driving down a road and they hit a small pothole. The semi-truck probably wouldn't notice it, whereas the F1 car might break an axle, right? So it's maybe a bit more brittle. And this is a slide I made in response to a recent grant application response that said, this is wrong. You need inertia for stability. Everyone has already known that. So I made this slide. Oh, sorry, I'll get to that in a second. I made this slide, which said that this is the inertia for inertia's sake solution, right? We're trying to make an F1 car act like a semi-truck, and that's not really what we need to do, right? So, it's kind of just to make a point, but this is a simulation I ran on the Kunder system with a master student at ETH, where we showed that replacing generators with IBRs can indeed produce oscillation. So if you're removing inertia and instead putting in inverters, and then let's say you have a fault, you get that dashed line that can oscillate, and standard power system stabilizing control will not stabilize the system. It turns out if you just redesign those power system stabilizers, because you still have two rotating machines, you can stabilize the grid. So this kind of brings it back to, if we do control right, well, we can handle a lot more inverters on the network rather than just throwing up our hands and saying, we need this.
Maybe, so from what I remember, the inverters, they will stabilize it because they have this rotating inertia, right? And so
Or the rotating machines will. The
Yeah,
inverters
so,
don't have.
yeah, sorry. The rotating machines, they have this rotating mass. So this is
It has these nice synchronization and stabilization characteristics combined with a huge energy buffer in that rotating mass.
right, which is similar to this group control, no? And this is
Well,
kind
it's related. So the swing equation and droop control are kind of the two parts that are the backbone of grid stability and have been since the first AC grid. So they work together basically.
yeah, but if you could, and the nice thing is that this reacts instantaneously, but without you needing to do anything. But if you could do the same, why could you not do the same with inverters if you
Yeah,
can
absolutely.
switch in fast?
I mean that's kind of the point that I'm making. That you can do droop control with an inverter, and then you don't need inertia. It turns out there's many considerations there. Because if you're responding very quickly, you might be exciting other dynamics. You have inverters interacting with one another. Everything on the grid is connected to everything else. So you need to be careful if you're driving around one car very fast, basically, or responding at a high bandwidth, basically, control speed. So this is the control theory solution. It's also what happens when you tell the LLMs to make the most Australian F1 car ever.
You just made them taller, that's it?
Oh, well, we have suspension and look at those wheels. It didn't put on a snorkel. Australians love snorkels on their vehicles, so you can drive through rivers or whatnot. I'll get that for the next presentation. But we're trying to figure out what exactly this control theory solution is rather than just a meme. So let's jump into the first application, which is the inter-area oscillation damping with an HVDC line. So this is when I say I will present a new control method that might be a good idea. That is on the right on this slide, basically. So on the left, we have the standard inverter control. So almost all inverters on the grid, in fact, probably every inverter on the grid is controlled with a box on the left where you have tiered or hierarchical control scheme with a low-level PWM control and then current control wrapping that. And then you have power control of some form wrapping around that. And that power control is doing some sort of feedback control. Maybe that itself has time-scale separation and hierarchy, but basically you're determining the input as a function of your output. And I put a Nyquist diagram there as a way of indicating that this is, I would call traditional SISO feedback type control, right? So you have various control loops and it works pretty well, but it might not be the control method we need because this hierarchy might be too slow, essentially, to your point. Instead, I'm proposing optimization-based inverter control. So it's essentially a time domain predictive type controller. So we have an MPC formulation here. Except for instead of the model, we just have the word dynamics model in brackets, right? And that will be the purpose of this talk is how do we figure out what dynamics model to use in our time domain optimization in order to control this inverter using an online time domain optimization. Is there any questions about this? Because this is kind of, I would say, the high level idea. Does it make sense more or less? Yeah.
Are you going to
Explain
the dynamics model or it'll be a simulator of some sort?
Oh, we're going to use it. We're going to learn it from data. You could simulate with it locally, but I mean, every MPC control action could be seen as a simulation of sorts, but it's local. And that's the critical thing is we're not learning a dynamics model for the whole grid. It's just the dynamics model at the point of interconnection of that inverter, right? So all measurements are done locally and then used to control the inverter at that point. So it's a local model. So I'll get into what I mean by that. But first, let's say why do something different. The first, and I would say this is really the key reason is that we have explicit output constraints. So these inverters can't go past a certain output current, and that is a critical limit of that hardware. So we can program that in explicitly, and that Y is in telegraphic Y right there. The second is that it allows for intuitive objective programming. So here we have the cost function, which is just a quadratic cost function. And if, let's say you're using too much control effort, you just increase that R matrix, or if you really need to settle faster, you can increase the Q matrix. It's kind of standard MPC or LQR motivations here. And then the third motivation is that MIMO is easy, right? So for standard Nyquist-based methods, they're typically SISO, single input, single output. Whereas the electric grid at any point of interconnection is at least 2 by 2 because you're working in a rotating reference, at least the D and Q components of the balance 3. So the challenges arise. One, how do we do prediction? And two, what is the online optimization? So the answer to the first one is that we're going to use data-driven predictive control. Yeah.
Can you say something about what the time horizon is? Because U is a vector, right? So I guess
Exactly. Yeah. So this asserts a time horizon, whereas in traditional feedback frequency domain type control, you don't have a time horizon. Whereas in MPC, you always have this time horizon. And the time horizon needs to be long enough to capture the dynamics or constraint violations that you care about, but not so long that the optimization becomes intractable.
meaning that it will be forecasted that.
Exactly. Yeah, exactly.
Okay, so it's a generic time horizon that we pick suitably for.
It depends, and it's intricately linked to the discretization.
So that was my next question. And then I guess discretization depends on switch because you switch them at 20 kilohertz also, right?
Well, we're going to go with a much slower switching frequency because basically these data-driven methods are not perfect, right? You can get, depending on the quality of your data, between 0 and 100 accurate, semi-accurate prediction steps, depending on your noise to signal ratio, right? So these are all, I would say, critical engineering questions, but they're per application, right? So we're going to present the method and then kind of shrug and say, well, the engineer should figure it out for the thing that they need it for. But it's absolutely critical. So here's a simplified HVDC line for folks who are not power systems engineers. The grid is AC. So on the right, we have an AC grid where we have 2 areas connected through an AC power line, right? So this could be Northern California or Southern California or Northern Australia or Southern Australia. They're connected through an AC power line. I guess California is a good example because in parallel to the path that goes through California, there's actually an HVDC line that goes through Nevada, right? So you actually have a DC power line in parallel with an AC transmission line. And what can happen is the 2 areas can oscillate against each other. Basically, you get coherent oscillations where all the rotating machines in one area swing against all the rotating machines in the other. And this tends to be in a certain low frequency band. And it's not uncommon. It's what we were observing in Europe prior to the power outage last April, where the Iberian Peninsula was swinging against northeastern Europe. Now, the idea is, can we use power control sent to inverters on either side of the HVDC line so that the inverter injections dampen the oscillations? And this is a problem that Hitachi is interested in because Hitachi builds HVDC, right? So if they can provide plug-and-play solutions to customers, that's of value to them. So this is their grid model that they use. This is a toy. This is not an actual grid model. It's just the Kunder 2-area system copy and pasted above and below, connected through one AC line and one DC line. So it looks like that system I just had up. And they have their proprietary HVDC inverters in their model. It turns out that access to those converter models depends on if what stage of engineer you are at Hitachi, right? So this is a core trade secret for Hitachi, how they control these inverters. So Giacomo, who's a student I worked with, described the model as super top secret. They never even considered letting me look at it. I wouldn't have wanted to anyways because I probably couldn't understand it. Whereas Mats and Jan probably can see it, but they're not allowed to share it. It's NDA, essentially. So the idea is, can we control these inverters at these high-level inputs, right? So can we give voltage references or power references at a higher level and then learn the dynamics of the lower-level controller and of the grid at the same time? So we're not just learning the lower-level controllers, we're also learning the aggregate behavior of the whole system as seen through the points of connection for this HVDC line, such that we can dampen the grid oscillations. So here we have a Nyquist plot that you could build if you had an accurate model of the system, which of course we had because we're just in the simulations, we're just researchers. And it turns out that as you deactivate the power system stabilizers on this network I just showed you, and you get up to 50% deactivation, you get some oscillations. You have a pole flipping over to the right half plane. And if you get up to 75%, you get a number more of oscillations. And this shouldn't come as a surprise. This is why we have power system stabilizers. The problem is you need an accurate system model to get this plot. And in practice, we do not have models of the grid of this accuracy, right? So when those AEMO engineers were saying, well, we don't know exactly what's happening, it's because they have a pretty good model of the grid, but then you actually have the true physical system, and there's always mismatch between the two. Questions? Keep going. Lunch was served, so I'm going to make some progress. So this is a talk. I'm now going to this is a talk I give from, or a slide from a different talk I give on the eras of control theory. It's kind of a fun history of control theory talk that makes the point that we're now in a new area of control theory where we've departed from the state space era where we worked with ABC matrices with a clearly defined state dimension, and we're now trying to control systems that don't have a clearly defined state or even state dimension. So if you're controlling an inverter connecting to the electric grid, you have no idea what the state of the electric grid is or even what dimension it might be, right? So we're trying to control this incredibly complex interconnected system, and it's not clear exactly where we would even start if we wanted to identify ABC matrices. So that's going to be this talk, and there are two types of data-driven predictive control methods. There's the indirect or more classical type approach, and then the direct, which is what we're going to focus on in this talk. So it's indirect, and this includes subspace identification, or if you've ever used the N4-SID algorithm in MATLAB, where you identify ABC D matrices up to some similarity transform. This is the more classical Leonard-Leung indirect approach where you're going through a state space.
But you still assume LTI.
Yes, and Gaussian noise, and that's what I'm really excited about, is getting away from such assumptions. But yes, critically, we do assume LTI still. And when we get to including empires, we're going to assume Gaussian noise as well. Yeah, I guess that's not the most critical, but the really limiting assumption is LTI.
Right, because inverters are not.
Inverters are not LTI, and that was one of the big questions. I mean, much of the world is like this. We apply LTI type methods, or frequency dominant methods, to non-LTI systems, yet somehow they tend to work.
So will you have, you just mentioned it's data-driven, will you have different models for different situations, and then you have like different linearizations of your nonlinear system?
Yeah, we had an L4DC paper probably being presented right now on that.
Okay.
So that's an active area of research, and it's a super exciting area because like LTI methods work, right? It's like, and they're somehow explainable, although the world isn't LTI, so it's always a given. So just a bit of background on what we mean by direct control. Here, this is a Hankel matrix. If you hadn't seen this before, essentially you're going to collect your data and partition it. You're going to line it up in time and partition it and take trajectories that are all L long. So L is some number, and you're going to take L measurements and put them in one column of your matrix, and then the next L measurements and put them in your next column. And you're going to do that. You're going to make this very wide matrix with a number of L long trajectories. And it turns out that for a noiseless, that this is actually a noiseless LTI system, all valid L long trajectories can be generated as a linear combination of what you've seen already. So if you shake your system enough and it's truly LTI and you live in some other universe where you can get noiseless measurements, then any valid system trajectory will be a linear combination of what you have seen already. This is kind of the miracle of LTI-ness, it's superposition. So the superposition can be used for control. This is the much celebrated data-enabled predictive control algorithm, which builds on top of Willem's fundamental lemma, where essentially instead of identifying the system offline, you just get this really wide Hankel matrix and you optimize over G online. Right? So you optimize over this linear combination vector that is linearly combining the columns that you've seen already, and somehow it's doing the system identification, state, estimation, if you will, or somehow localization, determining the initial condition, and optimization all in one pass, which is pretty cool, but also very expensive, right? So by including that whole Hankel matrix, you're carrying around this giant Hankel matrix and optimizing over it every single time step. So G can be a big vector, and this is a very expensive optimization. So it turns out that there are other representations of LTI systems. So we talked about state space and subspace methods. So what I just described is a subspace type method where you're optimizing over a subspace. There's also this other representation for LTI systems, which are ARX type models, where you just do single step prediction and you can iterate that single step prediction forward in time. And that will be or has been the focus of my work for reasons that I will get to. One of the big ones is causality, right? So if you're iterating this single step predictor forward in time, you know that an input at time 2 is not going to affect your output prediction one step in advance, whereas the subspace methods don't have that advantage. So these ARX type methods, what I've called transient predictive control, is a specific type of an ARX type method, is one way of doing it. So we talked about the CDC, but I'm not going to dwell on that in this time. So do the LTI methods work on this nonlinear system? So we're controlling the higher level reference points for this HVDC line here. And we tripped line 16, 17. So there it is. So we tripped this line and we want to see if controlling these reference points being fed to these lower level controllers can in fact stabilize the system. And it turns out they can, and it turns out the three different LTI data-driven methods all work pretty well. So Deep C works, transient predictive control works, and then another ARX type method also works. They work about as well as the method that was produced by Max, who's the senior research engineer at Hitachi, who had access to the whole model and designed a lead lag type controller, right? So that's the modal residue and loop shaping. This can be seen as, I would say, the industry standard type methods that are model-based. They require models to tune. And we're getting similar performance just from looking at what the data explains from the system dynamics. So this is encouraging and exciting to Hitachi because they know in practice they don't always have access to the model.
So a question here. So basically here, this linear model works, or LTI works extremely well. Can we also claim that it's because if we look at the system response, it's basically linear behavior is dominating.
Yeah.
Yeah.
So why is LTI working here? There's something I haven't mentioned yet, which is that this is high level control, right? And so you have many layers of lower level controllers. And one thing we know about control is that it keeps a nonlinear system in a certain operating regime, right? You're staying close to whatever point is being fed back to track. So in some way, it linearizes the system dynamics because you're staying in a local region. So I'm not asserting that this will always work on power systems. This is a big question. Do we need to come up with non-LTI type methods? I'm saying for this specific example where we're just changing the set points, it appears to be all right. And we tested it, and we tested the LTI-ness of it. It's in extra slides. Yeah, but that's a good question. That point makes sense. We're just kind of adjusting the references for lower level controllers, and therefore a nonlinear system starts to look maybe linear enough. But this isn't, maybe the final form that we want for all inverter control. So we're still pushing it. But it's nice to have a positive result.
Just a quick follow-up. So conceptually, are we trying to doing the secondary control typically for the system?
So secondary control, I think of secondary control as frequency restoration. Secondary control is really easy. It's like if frequency is low, inject more power till it's not low anymore. I mean, there are big challenges with secondary control, but the big challenging power system stability question is inter-area oscillations, both sub and super synchronous, right? So it's important to restore frequency, but more critically, we're just looking at the unstable dynamics that can arise without any sort of frequency considerations.
Which is, so here, like, I guess this is also predicated on this idea that you have this sort of like, cooperative control setting, right? Like where you are sort of setting settings for all of the lower level inverters and presumably they're following them and all of that kind of stuff. Like, for kind of both this method, but like also like the premise overall that like you can just sort of like not need inertia, like is that a requirement, or do you feel like in competitive markets there's also a way to somehow proxy this behavior?
Big question.
Yeah.
Right? Which is, if I'm understanding is, here we're just controlling one inverter. I haven't talked about the interaction between different inverters doing this, right? And we haven't figured that out yet, right? The idea of, if we think about it now, the rotating machines don't necessarily cooperate with each other. They just all have inertial responses that somehow inherently cooperate with each other.
Right.
So that's, and I'll get to this, that's why I think inertia is a really good place to start and might be good enough. Virtual inertia, I should say. So if we have all the inverters trying to act like rotating machines, we get this nice, I would say, cooperative type dynamic. That's not perfect, but it's a good place to start.
So actually, I might have then missed something about the setup of the problem. Could you go back again to like what was being controlled, what the setup, what the set points were there even out with like?
So this is a single HVDC line connecting two regions. And this is very much a toy, right? So there are no other actively controlled resources. And Hitachi's it owns both of these inverters on either side of the HVDC line.
Okay.
And they're talking to each other, basically. So
Okay.
this is centralized, you're right.
And so when
there are future scenarios if you think you could have an inverter at every single one of these buses, and they're not talking in any way, shape, or form, but they all are all connected to the grid.
Thanks. And so when you say, for example, like Hitachi was excited by this because there might be situations where they don't know like the full inverter model, like do you mean sort of like, for example, like a system where like this is a place where they would have white box access to the model, but like elsewhere on the system,
So Hitachi, I mean, it was kind of like a side point that they wouldn't have access. They don't have access to the model. Hitachi they are the model.
Right.
In fact, it could be argued that's their core business.
Right.
Is the dynamics model, which is proprietary, right? So they have access to their model. What they wouldn't in practice have access to is all the other dynamics on the grid.
Okay.
Right? Just because no one has access to that in reality, right? But so they know their inverter dynamics, but they don't know what's on the other side of that wire, basically.
Yeah, makes sense.
And that's really the critical aspect of these data-driven methods is you're participating in an unknown, Wild West type environment. And you have some obligation to participate well, but it's not your first priority, right? Whereas for Hitachi, if they're building these HVDC lines, it very much is their customer's first priority. And that's why it's an interesting application, right? Which is very different than the rooftop solar panel.
Right.
Which kind of doesn't care, but just wants to be stable.
Right. Yeah. No, that makes sense. Yeah, thank you.
Yeah. Other questions about this application? Because that's actually this isn't the last slide.
I think I missed it. So you mentioned these data-driven methods, right? How did you try to specifically excite the system to get certain dynamics, or how did you learn?
That's a very rich question, right? We're just using white noise perturbations, which in practice you wouldn't, perhaps. But system identification and all the optimal excitation questions, very deep field. The idea is to have something relatively robust though, so it should work with simple white noise excitation and work better perhaps with more optimal types of excitation.
How did so you kind of motivated this at the beginning, comparing to I forgot the name of them, but the rotating machines.
Synchronous condensers.
Synchronous condensers.
Yeah.
And so it seemed like even just you were saying this is in some cases, a large optimization or control problem that you're solving.
Yeah.
And presumably it seems like there might be additional hardware that's needed to do this type of thing rather than kind of
I'm so happy you asked that question.
okay. This should motivate your talk.
This is the second time you've done this. This is so great. I gotta learn your name. You gotta come to all my talks. So we're running this massive online optimization. We figured out one way of making it smaller by moving away from deep C and going to these ARX type methods. But can you actually run an optimization, in less than a millisecond, basically? So we need to be making with standard feedback control, you're making a control decision, at least every millisecond, right? So it turns out with these modern optimization tools, these splitting methods, we use OSQP and SCS, they are really fast and it's quite impressive. In particular, because we're dealing with LTI dynamics, so our constraints are LTI and our costs are quadratic. So we've made it as easy of an optimization problem as we can, but because we've done that, OSQP is able to solve the transient predictor. So this is the ARX type optimization on the order of microseconds. And it does all sorts of cool things like pre-caching the matrices for the KKT conditions and all this stuff, which I dove into after Giacomo produced this plot, because I said, there's no way it's doing this reliably, and I dove into, okay, there's some basis for it. But I think this is an important mind shift that we as engineers need to have these days, which is if easy optimizations are about as expensive as MapVex matrix vector products. Like this is about as expensive as a matrix vector product, and it's reliable, and you will always get a solution because it's convex, right? So there are convergence guarantees, and it's really fast. And so if we keep our optimizations to be quadratic programs, I think that's a tool that's still underutilized, and that's, I would say, one of my more abstract hypotheses that's motivating this work.
This type of controller designed for specific oscillation, the frequency of oscillation, because the inertias it's mostly stay there to handle all type of oscillations. Like especially in your setups, it's a wide area, so it could have some low inertia oscillations, low frequency oscillations, and particularly with the inverter converters, they have the high frequency oscillations. So I see your case study, I think it looks at, and also the online data so far is set up, it looks as if it will only work for specific, like say, high frequency oscillations.
So we're only doing subsynchronous oscillations. We're not doing any high frequency oscillations. It might work for those as well. That would be even more challenging, I would say. But we're targeting these subsynchronous and inter-area oscillations. And we're not actually targeting a specific frequency band. Traditional feedback control, traditional power system stabilization type methods target frequency demands, the frequency domain type methods, Nyquist plots, etc., Bode plots. This is a time domain optimization based predictive controller. So at no point are we saying, hey, we want you to get rid of this oscillation that's the dashed gray line here. We're just saying output flat real power and keep the voltage flat. And the optimization in the time domain is somehow figuring out how to stabilize these oscillations. So it's a different way of thinking about stabilization, and it's not as rigorous. It's like an MPC type approach, but still somehow, like the modal residue, the loop shaping methods, these are the traditional industry standard frequency domain type methods. And, TPC is some time domain optimization using a data-driven method, and they're producing similar stabilizing behavior, which is, I think, surprisingly cool. That's a good question. Thanks.
No, I think I had a similar comment. At no point in your controller does it know it is doing any oscillation mitigation.
Bingo.
It is just trying to make sure that the bounds of voltage and injections are satisfied. You're following that set point, right?
Yeah. Which is weird. It's not how we've ever done stabilization. We've always said target this frequency band, which we know to be unstable. But to do that, you need a system model, right? Or at least a Bode plot. and so, we're going with the time domain. You could produce a Bode plot, but we're just staying in the time domain. We do system identification, output constant real power. And that's why you know, it's surprising to folks like Hitachi guys. I don't know. I guess this works, but it's a bit unnerving to them. But if it works, it works. So you got to push it until it doesn't, or hopefully we can get it into the product. Okay, I'm gonna keep going. So yes, for the outer loop control of this system, the LTI data-driven methods work about as well as the model-based methods. And we didn't try and say this data-driven method is better than this other, because there's so many hyperparameters that you can tune. I don't want to say, oh, this one, mine's better than this other person's. It's more just a general point of like, hey, they're working pretty well. Let's keep pushing on this and see where the limit is, because it's not here yet.
Okay. So I guess it's difficult to prove this because you don't have a model.
And generally, it's like, what do we have in time domain model predictive control? We have like recursive feasibility type results and things of the like. So it's a bit unsettling, I think, to traditional power system or both power system and control engineers. I give this talk and people read it. I don't know what to make of it, but it worked.
Question. So I know that in your previous book, you guys also work with standards and if you have gone to that direction, right?
Yeah.
So when you think of a particular control method or algorithm to get it implemented into a real inverter to be bought by the standards organizations, what do they want? Are simulations enough, or do they want theoretical guarantees?
It depends on where you are in the world. AEMO has, I think, a really innovative approach to good connections, which is they just have a set of benchmark tests and say, look, you need to do this well in the benchmarks. Other method or other I would say there's not a lot of unity amongst the various TSOs about what it means to get it incorporated into a system. So it's a bit unclear right now, I would say. But there are some grid codes that are just benchmarks, and if you do well in the benchmarks, then there you go. So that was optimization cost. And this is just making the point that it's fast enough, right? So we're talking about dynamics in this range, controlling inverters in this range. So the optimization sits in this range. We're good to go. So now we're going to do a bit of an interlude on Bayesian predictive control. So this is the control theory that I've been working on. So this is a departure a bit from power system theory. And the motivation for Bayesian predictive control, or the Bayesian approach, is that we care about performance on the real world system. We don't care about performance on our model or on our maximum likelihood estimate from data, right? So you have your maximum likelihood estimate, you have your model, whatever. When you put it on the real system that generated that data, how will it perform? And we're also in a noisy world where your maximum likelihood estimate is going to be wrong. So this brings us back to the indirect and direct distinction. And here we make the point that the indirect method, I'm going into a bit more detail, you gather the data, you then use the data to do system identification, and then that system identification is used in MPC, and then also you have a Kalman filter. So this on the column on the left is kind of a standard LQG or system ID plus LQG type approach. But we know from this celebrated paper that this is not robust, right? So just controlling for the maximum likelihood estimate of a model might not actually stabilize the true system dynamics, because Kalman filter plus LQR can actually be very brittle in terms of its stability. So can we do better if somehow we stay in this direct domain? And that's essentially the promise of what I've started calling Bayesian predictive control, where we're going to use both data and external information. That's any sort of bias about what the system dynamics might be or hypothesis about the system dynamics, and you fuse them into control using Bayes' rule, essentially. And what we're after is the expected performance on the true system. So this is your cost function for the true system. This is your true output conditioned on the data you've seen. And implicit here is you have a prior. The prior could be informative or uninformative if you don't have a prior. But ultimately what we're interested in is this performance on the true system dynamics conditioned on data. So why Bayesian? The first is that accounting for uncertainty. So you've learned system dynamics. Accounting for uncertainty will give robustness. And then the second is that you can use external information and data. So rarely are we in a system where we actually know nothing about the system dynamics at all. We might assume they're, stable or somehow smooth in some way, or perhaps we know it's a double integrator and we just don't know the mass. We would like a mechanism that can incorporate external information. So first, let's talk about accounting for uncertainty and how that might give robustness. I don't think we'll have time nor interest to step through the specifics of the math on this slide, so I'll just go fast. But basically, this is the stochastic optimization we care about, but can't actually solve, right? So we have this conditional expectation, and it turns out that can be solved approximately by a regularized deterministic problem. So we just take the cost function applied to the a posteriori estimate of the system, which we got through Bayes' rule. So this is where, in some way, we're incorporating our prior and our maximum likelihood estimate and crunching that into a single a posteriori estimate. And then we get this other regularization term. So these results, I think, you basically always see them in machine learning and control because it gives us something we can actually optimize over. We have the problem that we care about, and then somehow we end up with just a deterministic optimization with this additional regularization term, which is nice because that regularization term somehow reminds you that you don't actually know the system dynamics with certainty, and you need to account for that uncertainty every time you make a control decision. So accounting for uncertainty gives robustness, and then the second point is that if we combine external information with data, we can really reduce the data's explanatory burdens. We can reduce the lift that data has to perform. And here we have the multi-step predictor is actually this very large matrix with 720 singular values, or 720 by 720 in terms of all the, in this specific example we looked at. But if we just recognize the structure of the system and say it's somehow stable and smooth, the singular values we care about is down to 66, right? So by just asserting inductive bias about the system, we're somehow reducing what's the data is expected to explain. So this is, I know I'm just kind of brushing over the top of it. It's not the main purpose of this talk. We can talk offline in more detail. This is an example showing that these priors can really help. So this is for a very simple double integrator system. And here we have the stable spline prior, which improves upon the maximum likelihood estimate here. Asserting that prior helps. And then if instead you knew everything, or if you just didn't know the mass of the system, so let's say you're controlling a double integrator and you just didn't know the mass, you can get your prediction error to almost zero by asserting the system dynamics. And that's what's, for me, really exciting about this Bayesian type approach, is that it's a way of fusing, these data-driven methods with what you know about the system dynamics already. And it's in some way a recipe, so it can work on many LTI systems. And hopefully we can extend it past LTI systems. And then finally, chance constraints on the true underlying system. So that's why we're doing these predictive methods to begin with, is that somehow they can incorporate constraints on the output. And once again, we have the problem we would like to optimize, which is this constraint. However, we don't know the output of the true system, so we end up with a chance-constrained problem here. Through that El-Gawi method and Calafiore from the 2000s, we end up with essentially a tightened deterministic optimization that gives us guarantees for the chance-constrained problem. And what's really cool about this is that tightening is learned from the data itself, right? So we're not just trying tightening, oh, that wasn't it, oh, let's back it up, move it forward. We somehow have a principled way of tightening our constraints so that the true system doesn't violate the output constraints. So I'm pretty excited about this predictive control method for power systems, and then actually beyond power systems as well. So that's the control theory stuff. We're getting back to power systems. We're also running out of time, so I'll keep going fast. This is single inverter, or I should stop. Are there any questions about this? Okay, let's keep going.
The chance concerns are around the modeling inaccuracy, right?
It's the a posteriori, I should be able to say that word, accuracy.
That's fine.
Yeah. So it's the combination of your modeling or inductive bias and the informativity of your data. So you crank those through Bayes' rule, and you still have an uncertainty ball on your prediction, and it's a chance constraint on that.
But it doesn't have, let's say, in real time the measurement that you are getting if that has errors, because I think you can also do that, in fact.
There's many ways, but it's not.
So it just it's.
I mean, but somehow it knows that the measurement that you've just gotten is uncertain. I mean, I would say it's like a comprehensive uncertainty, because baked in your training data is the fact that that measurement you just got is going to be noisy. It's all baked in, right? Well, I mean, I can't ask you that. Yeah, I'll have to send you a paper before I say that. Yeah. So it's all baked in, which to me is exciting. It is still for LTI Gaussian noise system, so exciting to extend past that. Other questions? Okay, let's get the talk done and go to the full question session. So back to power systems. That was the HVDC line stabilization that we talked about previously. Now we're going to talk about single inverter control. So here we have rotating machines and inverters. And if you're not a power electronics engineer, a really critical thing to understand, and something that the power electronic engineers always jump up and down on the table and yell, is that inverters have constraints, right? So you can't go above 1.2 the rated current. At the end of the day, it's a switch of some form, and that switch gets too hot if you put too much current through it. And so all these inverters, this is, I think, a very large inverter, have strict current limits. And that's one of the reasons these predictive methods, and we're worried about constraints when we're actually controlling these systems. It's one of the real benefits of these predictive type methods rather than the frequency domain type methods. So this term feasible VSM stands for feasible virtual synchronous machine, and it is an inverter providing virtual inertia. So this is what we talked about, without violating inverter constraints. So do your best to act like that thing on the left, but don't melt, basically. And inverter control has traditionally used PI loops. This is true for a number of reasons. The first is that no grid model is available often, but PI is super robust. The downside is constraint violation. So PI control doesn't provide constraint guarantees. So what gets put in practice are saturation blocks and other very clever engineering tricks, such as virtual output impedance. However, these things can interact with each other. Virtual output impedance, saturation blocks, you're adding nonlinearities that are not otherwise accounted for, and it can lead to undesirable effects. So we'd like to avoid using that. The traditional approach to avoiding constraints is model predictive control. We talked about this a lot, so I'm not going to dwell on it. Practice, we don't know the A and B matrices that describe the full system. In particular, we don't know this one, right? So we don't know the whole grid that we're connected to. So what do we do instead? We do these data-driven type methods where you gather data from the system, from just perturbing basically that inverter, whether it's a small or large solar panel or battery, is just going to shake the system and observe what it does in response, gather that data, put it in that data repository, and then use that as its predictive model. And then the cost function is somehow going to act and provide a rotating machine response plus droop control. So this is really the backbone of stability. The grid, and here we have an example where a fault strikes the grid in simulation, and we have these dynamics that could otherwise lead to issues or constraint violations, but this predictive controller, here we're controlling the green block, is able to keep the current below that maximum current. So in this example, DPC inverter control avoids constraint violations after the fault. So does it work? Here's some hardware tests we did at ETH. Sebastian is a master's student who I supervised, who really did an awesome master's thesis and showed that running this data-driven optimization on just a 35 euro piece of hardware, this is taking advantage of modern hardware and algorithms, we're able to successfully control this inverter in the lab. And so afterwards, we went to TU Munich after meeting Anurag at PSCC, and we controlled his Exton 25 kilowatt inverter, which was connected to the Munich electric grid. And this was, to my knowledge, the first time data-driven predictive control has ever been connected to an actual electric grid and all the dynamics that come with it. And sure enough, we were able to track the output. There are many more tests to do here, but this was a promising preliminary result on this specific case. So that's where we're at. The big question, I promised you a big, exciting research question at the end, and here we are. What objective function should we use, right? So up till now, I've been talking about virtual inertia or feasible virtual synchronous machines, which is, well, the grid has always been stable more or less because we've had an inertial response plus droop control. So let's start with tracking that. However, that looks a lot like this if we're thinking through analogies. Does anyone know what this is on the right? Yeah.
I guess this is the first car that
very good.
that his wife drove for 30 kilometers from.
Yeah, so this is I think one of the first automobiles. It's actually an electric car, right? And it looks a lot like a horse-drawn cart because up till that moment, that's what we knew about mobility, right? Carts are mobility. So if we're going to make a car, it should look like a horse-drawn cart. But just 20 years later, we have this, right? Which looks very old and cool, but like a modern automobile where you have the engine in the front and the seats in the back and the steering wheel, right? So form fits function, function fits form. We have to figure out what that means, right? So I think starting with virtual inertia and droop control, droop control is definitely a good idea. Virtual inertia is probably a good idea, but perhaps we can do better. And this is the kind of research question that I'm really excited about, which is how you have all these self-interested inverters that just want to be connected to the grid. How do we control each one of these inverters or somehow create bounds with grid codes such that when they all participate together, we get a stable aggregate response? Okay, thanks so much.
Thank you very much, Index. We go back to the point when you discussed the time scales, the different time scales of optimization and control in the grid. And you always see in Power System, there's kind of two groups doing optimization and control. Those that are in the steady state.
Yeah.
And then they assume that I'm sending set points to some control algorithms and they will take care of it.
Yeah.
Similarly, from the dynamic side, they're saying, okay, we're going to receive some optimized trajectory that I'll just simply follow.
Yeah, and these people have never talked before.
Exactly. and then due to that, you reach a lot of suboptimalities because now the multi-period OPF folks, they give you 2 points and then they assume that there exists a feasible trajectory between these two consecutive points.
Yeah.
And then same for the other side, they just try to match these consecutive points. So relative to the last point that you said, what is the objective function?
Yeah.
I just want to hear what's your thoughts on these two.
I mean, it's a very good question.
Because with data driven and inferencing, the time scale is closing up.
Which is, do these two groups need to talk more, right? Or should they talk more? And I think yes, but it's important to remember just the breadth of timescales that we're looking at, right? So nothing I talked about today is on the order of minutes, right? And even the fastest markets are, we're talking about 5-minute clearing, right? Because that's what's computationally tractable. Now, I think you can really improve performance if somehow the market's considered stability in some way, right? Or, there's talk of inertia type markets. And this brings up really rich questions, which is kind of what I'm nudging folks on or trying to, which is, does an inertia market make any sense? The main reason an inertia market makes sense is because we understand it. Turns out that's actually a very good reason to have one, right? Understanding what's going on is worth a lot. So I don't want to say that that's bad. I'm just kind of pushing on that and say, well, let's make sure that's what we want. And I think that to the extent that the two parties at least understand what the other group is after, or what the binding constraints are, I think it's going to lead to more efficient grid operation. The important thing because I also often wear a market or online optimization type hat. I really love that work as well. The important thing to remember is there's not really a dollar value on a power outage. When you have power outages, it's like a plane crash. People die, right? So So markets are about efficiency, but at the end of the day, there's kind of a line you don't want to cross in terms of stability and these sorts. So it's an important thing to remember just about the importance of resiliency and always having the lights turn on. Yeah, so there's different time scales, there's different value scales, and there's all sorts of things to consider that make it a very rich research problem that everyone in this room should work on super.